somehow a part one talk, because Cora will talk about this tomorrow too, and she will present all nice plots and amazing results, I imagine. So I will talk more about the mathematical part, so more on the large deviation theory and how it can apply to large deviation theory to large-scale structure cosmology. So let's assume that there is a universe with large-scale structure, and we can choose a matter content, initial conditions, and a theory of gravity, and try to reproduce, understand how structure will form in this universe. And if we are skilled enough, we can know how the dynamical system will evolve, and we can compare the statistical properties and the nature of the large-scale structure we get with the one that we assume to exist in our universe. But there are plenty of specialists in the room in the point 1, 2, and 3, and we know that even with very simple assumptions on matter content, initial conditions, and theory of gravity, we get a formidable and nonlinear and complicated problem on the growth of structure. So to get things simpler and in a way that we can approach with analytical methods, we will assume configuration with spherical symmetry. I will choose matter to behave like an ideal pressureless fluid, and I will look at Newtonian gravity or general relativity or any theory of relativity that respects the Birkhoff theorem. Only matter inside the sphere will interfere on the evolution of that field. And considering this framework, we follow exactly on the classical solutions of spherical collapse. So we can ask the following question. Assuming that we have a primordial field that is a Gaussian random field, filtered over a sphere of a given radius little r, that evolves under the influence of gravity into a nonlinear density rho inside another sphere of radius r, because I'm assuming spherical symmetry. How the statistical properties of that field will change under the influence of gravitational field. And as Sandrino showed just before, the PDF that was for that random variable tau, that was Gaussian, start getting asymmetry and flattening by the action of the gravity. And if you want to parameterize the final PDF, you need to have the full set of coefficients that are the cumulants, the skewness, kurtoses, and you have actually an infinite series of them that will fully characterize the final distribution, the final nature, statistical nature of rho, that is the matter filtered inside that sphere. And this has been studied for a long series of papers, most notably by a series of papers by Francis Bernardo in the 90s, and then Francis and Patrick and Sandrine and so on. And actually you can compute the full series of cumulants and compare with measurements in simulations and reconstruct the PDF for the nonlinear density field at the limit where you take the variance to 0. And this was mostly done in perturbation theory. So I can see things there, it's easier. You can do this in perturbation theory, and you see emerging structure on this problem. There are series of ingredients that appear repeatedly, even if you change the formalism and so on. And it seems, reading the literature, that there is some structure behind that allows the problem to be solved the way it is solved. And we converged into a synthesis of this problem with Francis on this paper, relating this formalism to mathematical theory, a branch of theory of probability, that is the theory of large deviation, that appeared around the 40s and was strongly developed in the 70s with applications to random processes in general, theory of partial differential equations, stochastic processes, and so on. So it is a huge field now inside the probability theory. And we will apply this to the problem of large-scale structure. So this is what I'm going to do in my talk. First, I will show you, since I'm talking to physicists, that you all know theory of large deviations already. But in any case, I will show you what is the formal definition of it and a few consequences of the large deviation theory. And then I will obtain in one slide all the cumulants for the nonlinear density as I described, and show that the use of large deviation theory is not only needed to rewrite and reobtain things that were known before, but you have a strong power of generalization on it, and I will show how to get the cumulants and the PDF if you have more general filtering than just top hats. So assume that you want to smooth your filter, your field by a Gaussian filter or things like that. So just to establish some notation here. I will start with the classical problem of dice rolling. So if you have a fair dice, and you can have the results of 1, 2, 3 for one dice roll, and the probability of getting any one of those is 1/6. So have here 1, 2, 5, 6. If I roll it twice, I can get my configuration space, the space of all the possible results of this result will be lambda times lambda, the Cartesian product. And I can get, say, like 3 in the first and 2 in the second, and so on. If I roll this dice n times, this will become a weird cube here in n dimension, and my configuration space will be lambda to the power n. So this is what I'm drawing here as this funny surface. And what is the probability of getting some set here A? It will be 1/6 time to the power n, that is the dimension of this space, times the cardinality of my set A here, like the number of elements that I'm putting inside it. So this is this lambda n is my configuration space. Then if you can define a probability measure on this space here by 1/6 to the power n times the cardinality of the set. And the probability is a map between this space and the interval 0, 1. In mathematics, actually, it's not the probability is not actually defined on lambda n, on the configuration space, but on a sigma algebra defined on this space, but we'll jump this part. So the space itself plus the sigma algebra is a measurable space, and the probability is a function with nice properties that is defined there, and the set of the three of them is a probability space. So always think this, but let's take simple. Then, okay, I have a configuration space, and I can define probabilities that depend on n, because I'm on space on n dimensions. That is a map from this space to the interval 0, 1. Now I can ask, what is a random variable here? A random variable is a map between my configuration space and some other space that may be an interval or another complicated metric space, whatever. Here I'm considering the sample mean. So I will get, say, 3 and 2. I add it, makes 5, and divided by 2 is 2.5. It would be the results of my experience here. So I sum the coordinates of a point in my configuration space, I divide by n. And this is a random variable that is a map from my configuration space into an interval here on the rationals. And then I can ask, what is the probability that my random variable lays inside some small interval here? How I compute this? I take the inverse image of this interval by my random map. I get an interval on the configuration space where the probability is defined, and I get a map to the interval. So when I say that the probability that the random variable is This, I'm taking the composition of two maps. Okay, this is just to set the notations here. So what happens if instead of looking at dices, I take gas in a volume isolated at some isolated ideal gas, like in statistical mechanics. Then my configuration space is the configuration space or the phase space of this gas with the particles and velocities to all my particles. I take a random variable that is the average kinetic energy. Here I'm taking all particles to have mass 1, but you have the average kinetic energy. That is a map from my configuration space into an interval. And I can restrict my energy into some small interval here that I will call energy sandwich. And I will look to all the states in my configuration space that are compatible with my energy restriction. And I will establish a probability measure on those kind of sets. So there is some probability and so on. And this probability constrained to intervals compatible with some energy is what we call the microcanonical ensemble in statistical mechanics. This is things by Boltzmann. Then if you have your microcanonical ensemble, you can look, you also attribute equal probability to all the states that are compatible with some level of energy. And then what Boltzmann did was to look at the multiplicity or the permutability of all the states compatible with some level of energy and rank them by the rareness. So what's the probability that all the molecules in this room will concentrate in a corner and will die asphyxiated? Like, this is very small. The highest probability corresponds to states that are most random or you can obtain by many different possible ways. And all the others, even if they are compatible with your energy selection, they are suppressed. They are increasingly suppressed because they do not correspond to the maximum of the entropy. And the entropy is the thermodynamical quantity that will appear on the thermodynamical limit, and it is the quantity that will make the selection between all possible microstates possible, the ones that will be observed in nature. So what Boltzmann is doing is this here. He's looking at the probabilities. The probabilities on his microcanonical ensemble for configurations compatible with some energy he is requiring, but is the specific entropy. And when you take the limit n to infinity, what never happens in reality, you never have an infinite number of particles, but this is a thermodynamical limit. You claim that this limit exists, and this limit is the entropy as the specific entropy. And in the physical state, in the thermodynamical state, what you observe is only the maximum of the entropy. You never observe weird states where all the gas concentrate in some place. So equivalently, we can say that the probability for configurations that are outside the mean value for the gas that would be here, if I take my interval k to be here, it will be suppressed exponentially, because I have a log here, by the entropy. So entropy suppresses all the possible states that are not the physical one, the one that corresponds to the peak. Here I'm writing minus I to the entropy because it's more logical to do this, and even Boltzmann, when he writes his H theorem, he considered minus the entropy, and thermodynamics is like this. So this is classical statistical mechanics, and this is the basis and the full story about large deviation theory, as you see. Also, here I'm saying that I'm telling you, you have to compute the entropy. And how you compute the entropy? by defining this quantity, the log of the exponential of the energy times something. This is the partition function, right? And once you have the partition function, what is the entropy? It's the Legendre transform. So you compute the free energy, you take Legendre transform, you get entropy, and the entropy is the quantity that modulates the probability of getting weird or non-weird states. And once you have the free energy, if you take its derivative, you get the mean energy. If you have the second derivative, you have the variance. The third and the fourth, and all the derivatives of the free energy gives you the successive cumulants for your theory. And all of this is statistical mechanics, classical statistical mechanics. And also we can talk about convexity properties or concavity properties for the entropy and the free energy. I will write everything with a minus sign because it interests me. But the entropy in general is a concave function. So minus I will be convex, will be something like that. And if I have this kind of entropy, I can take the Legendre transform and I will have some other quantity for my C, my free energy. If I have this entropy, I will have this I. I will have this kind of C if my function is convex. Here I will take Legendre transform. If I take, so I star equals C. If I take I star star, that equals C star, this is equal to I, if my function is convex. If the function is convex. So you can be fancy and say that convex conjugation is an endomorphism on the space of the convex function. But if the entropy has not to be convex always, you can have phase transition that is associated to unstable regions. And it corresponds to places where the concavity changes. So I could have an entropy like this for a van der Waals gas or something like that. If I take the Legendre transform of this, I'll get something that has a point where I can't define the derivative because you have places that is non-convex. And if I take back my star operation here, what I get is only the convex envelope of this curve. And this is essentially the basics of Maxwell construction in thermodynamics, where you take equal area and so on to construct free energy and entropy for unstable regions where you have phase transition. So all of this is thermodynamics. But it is also all the basics and all the foundations of the theory of large deviation. But if you open a book on theory of large deviation, this is the definition that you get. And it's instructive to read it. Here I'm not writing, but X can be any kind of complete separable metric space. So a sequence of probability measures satisfies what we call large deviation principle if there is a function I that's lower semi-continuous. This is if you have a function that does this, then this point belongs here and not there. It's open, the point is there. Always you have left continuity. Well, left sets are compact and so on, and you have two weird and funny inequalities that look like the one that Boltzmann derived. And this is because you may want to apply large deviation theory to very complicated sets of space, for example, to describe random processes and all these things, and the complexity grows and you need robust definition. But also because these two inequalities here somehow assure that you can have weak convergence to this families of probability measures. When I say that these probability measures converge to something when you take thermodynamical limit, I have to say how they converge, because we are at Institut Henri Poincaré and they want to converge weakly. And to assure weak convergence, these kind of inequalities are needed. And essentially, you are looking for weak convergence for a family of probability measures that is not exactly related to it, but to an ansatz. You are assuming that they will have exponential decay. So this is a kind of assurance of weak convergence to these families if you have this kind of exponential decay. So this is the formal definition of the large deviation principle that you know already because you know statistical physics. So given this funny definition, I could ask two things. Are the families of probability measures verifying this definition, and what does one gain from this kind of definition? I have still so I will jump these. I will tell you, for example, that yeah, there are families that satisfy the large deviation theory, large deviation principle, and one of them helps us to understand the thermodynamical limit that I just presented before. And this is the Chromers Theorem, and is the first theorem proven in this field, essentially. If you have a set of identical or independent, identically distributed random variables, and you define C as the log of the expected value of the exponential of your random variables, or the free energy, then the large deviation principle will hold for the sample mean with rate function that is the Legendre transform of the rate of the free energy. It means the entropy, exactly as in the thermodynamical limit. And the reason for that I could explain, but it will save time, is just an inequality, a classical inequality in theory of probability, that is the Chebyshev inequality. Then you have that they are identical and independent and identically distributed, and you can plug everything else inside an exponential and you just get that. This is of course not the proof of the theorem. This is one part of the argument that proves one of these inequalities here. The proof is long and complicated, but at the end you get that if you have n identically independent, identically distributed random variables, large deviation principle will hold for this random variable with the rate function that is the Legendre transform of the free energy. And other thing that is very important, and it is how you can produce families of measures that satisfies random large deviation principle, is that if you know that large deviation principle is valid in one kind of space, here, say that in this space X, I know that I have large deviation principle with a good rate function. Then I have a continuous map from this space into another. Then this is the theorem contraction principle. Large deviation principle will also hold on that space Y with for this family of probability measures Q that are the composition of f minus 1 p, and it gives you the rate function. And how you get the rate function? You look at the pre-image of sets in Y by f, so f minus 1 in A will be, say, 2 sets here, and I look at the rate function that is less stringent for all the possible elements in the pre-image of this. And this will be the rate function associated to the large deviation principle upstairs. So in the words of Der Hollander, that is a mathematician that wrote a classical book on the field, and large deviation is done in the least unlikely of all the unlikely ways. So you look at the less stringent way to dominate the unlikely events to happen. So I go back to the problem that I announced at the beginning, or to a small generalization of it. I would take instead of one sphere, I will take a set of n concentric spheres in my initial field, initial Gaussian linear field, and I'll allow them to evolve under spherical collapse. So my random variables are defined as a filtering of my Gaussian field, my realization of this field. The final densities are given by a map that depends on tau I, that is given by the spherical collapse dynamics. And my matter conservation, I can associate, given that I know tau I, Ri, and ρ, I can determine the big R here. So I have my initial field, I have this map that is given by the spherical collapse, and I can define all the densities and the radii for my density, for my final configuration. Sorry. Then this is how you get everything from in one slide from large deviation theory. First, this is a set of Gaussian random variables. For Gaussian random variables, you know that large deviation principle holds, because if it doesn't hold for Gaussian, we have a problem, but like, you know it is a theorem. And I know what the rate function is, or what the entropy is. Gaussian, remember, you want always to say that the probability scales like e to minus n times the rate function, and Gaussian is exactly quadratic exponential minus something squared. So the rate function is readable directly. And here I have the inverse of covariance matrix, because these are non-independent Gaussian random variables, because surely tau 2 depends on the density that is in the inner sphere in all of them. So you have to have a covariance here. Then you have a one-to-one map that is the spherical collapse between the linear densities and non-linear densities before shell crossing. I am always talking before shell crossing here. So the large deviation principle will also hold for my non-linear family by the contraction principle. And I know how to compute the rate function for them. It's just to take the inf of this quantity under the restriction that the non-linear densities are given by my one-to-one map of the linear densities. So it's the same shape, but I inverse this relation to write tau as tau of rho here. And then the Varadhan lemma is one slide that I jumped. It tells you how to compute the partition function or the free energies. If you have these complicated integrals and sums to do, this theorem and the theory of large deviation tells you that in order to obtain this, the free energy, you just have to make a Legendre transform of your rate function, exactly as in statistical mechanics. So I will just make a Legendre transform of this quantity of my rate function for the nonlinear fields, and I get the generating function for all the cumulants of this quantity. And this, yes. So if I make in 1D, if I make a Taylor expansion of the free energy of the generating function for the cumulants, the coefficients in the Taylor expansion are the reduced cumulants for your theory. Just to show how they look like in 1D, the rate function will be something like that. The map given by the spherical collapse is very simple quantity, and you just plug everything in and you get what the rate function is. And just as I announced here, you don't have the same concavity everywhere. It changes, it has a critical point somewhere in the middle, and the free energy will be something like that, that it's defined in some interval and then it jumps. But the importance is that it is defined and you can differentiate it at 0 to get all the cumulants. But to the inversion and to get the PDF, this inversion and this critical point is complicated, and you can read about it. and see Cora's talk tomorrow that she'll probably say how this change in convexity makes things complicated when you want to get the PDF back. But if you only want the cumulants, you just get all of them computing these things. So that's why the theory of large deviation is important in this context, and it really captures the mathematical structure that is behind. But okay, we know how to do filtering with concentric spheres. Now I want to do more complicated things, like making a Gaussian filtering of my initial matter density. But I can say that I can write my Gaussian as a set of weights times my densities on my former spheres. So I do some I fit little blocks under my Gaussian to write it like this. Then I write, just because I can generalize, this is also a continuous map of this, that is a continuous map of that, so I can pass from here to there, write my free energy as also an extremization problem on my composed filtering minus my rate function that was defined before. And I can go through a continuous limit on here. My sum can always be expressed in terms of a radius, of those radius that are function of my initial taus, and the densities that are functions of those radii, and so on. So you get a functional dependence on tau here. Your rate function will also become a function of tau. And what you need to do in order to get the extrema of this quantity and calculate the sup, imagine that the sup will be an extrema, is to take the functional derivative of that quantity with respect to the initial field, n equal to 0. And if you do that, in this case, for example, you can obtain explicitly a nonlinear integral equation that determines the field configurations. And if you get to solve this, you plug back there and you get the cumulants for your Gaussianly filtered field, as long as you can solve uniquely for h lambda this integral equation. And now I can show you the only plots in my talk. Here is what you get for S3, like the skewness, if you have Gaussian filtering. The 4 points here are obtained by a tour de force on this paper, where they can integrate the Gaussian filtering and spherical Bessel functions and so on. But we could only get these 4 points because the integrals are extremely complicated. And doing this trick that I showed you before, you can get the full curve for any, I should say, P for me is something that is proportional to k to n, and this is this n, okay? So I can get for all these indexes, I can get the skewness for a Gaussian filtered density. And I can do things even more complicated and do the same analysis in the case of weak lensing. In weak lensing, everything is the same except that you project everything over the line of sight. And for example, one of the interesting measurable quantities is the aperture mass. And for the aperture mass, you have to filter your convergence field with a compensated filter that is something like this. So these filters U, they are complicated. You can choose from a family and so on, but they are not top hat. So how to do and how to analyze the statistical properties of the aperture mass if the filters are complicated? Well, the same extremization process can be performed, and we can get the cumulant for all of these things, and we can do even better, and we can, like, of course, I get this from this curve, but I can reconstruct the free energy for the convergence field, for the shear field, and for the reduced shear field. The reduced shear is gamma of 1 minus kappa. So it's n kappa and gamma are functionals of my initial density or projected density. So this is a very nonlinear and complicated stuff if you want to determine the statistical properties. But using this formalism and the generalizations that we can do, we can reconstruct the free energy for the reduced shear and show that it has different critical points, and you can also compute the skewness for it, and has a small difference to what you get in weak lensing theory if you assume that the shear is measured and not the reduced shear. So this is what I wanted to tell you, and I leave you with this.
Thank you. Excellent.